All right, welcome to our first online only lecture. Before break, the last lecture we had was on telescopes. We were also supposed to talk about the wave nature of light. So today we're going to talk about aberrations, which has to do with the optics we've already seen with telescopes and microscopes. But then we're going to talk about the wave nature of light things. Interference and diffraction are the things specifically we're looking at today. So before we get started, a couple of reminders here. Reading assignments, there's no change in the reading assignments in that we're going to have one assignment per lecture, but I'm changing the lead time from 1 week to 2 weeks. So you probably noticed today that I set up some changes so that you have a reading assignment that is due on Monday. I believe it's March 30 is the next one coming, but it's available now a week in advance. And I will actually have them generally 2 weeks in advance when you'll know. Also, we're going to have some lectures on Thursdays. I talk about that later. And so you'll have a reading assignment due for those Thursday lectures as well. Please do the reading assignments before you listen to the lecture. It just takes away some of the pedagogical reason for having the reading assignments if you do it after you've already listened to the lecture, after you already have the answers. The idea is for you to think about these things and try to understand it. And the things you can understand, then you can get more out of lecture. Okay. Second, the 3 Thursday lectures, because they have kind of changed since we last met, the requirements for us that we need to have one less week in our semester, but still have the same number of classes. So I've added 3 Thursday lectures starting next week, not this week, to help make up for that. Homework, there's no change. There's still one assignment per lecture, but that means that if we have a Thursday lecture, we're going to have an additional homework assignment that week that we'll do. So you'll have a homework assignment due Wednesday from the Monday lecture, Thursday from the Wednesday lecture, Friday from the Thursday lecture. So it's a little bit more compacted in that way. Laboratories, I still haven't set those up, but so I'll just move past that. The exams, because we extended spring break by 1 week, the next exam, instead of being on April, I don't know. I don't remember the date, but it's going to be on April 7 now, that Tuesday. I will be sending out a Google Calendar thing for you to sign up for 1 hour oral exam slots. And it will be a little different, but it will take less time for you. It'll take a lot of time for me. And it should give me actually a more accurate way of grading what you know, because some people do well on tests and some people don't. But when you're doing the oral exam, it's a little more, it allows us to evaluate what you know. Office hours, I will be available with email, but I will also be available on a Zoom channel for us to interact Monday, Wednesday, Friday during our normal lecture times, which is 11 a.m. Central Daylight Time. So no matter what time zone you're in, remember it's 11 a.m. our normal class time here in Lincoln. Each Monday, I will send you I'll put a post on Moodle that will come to you as an email with an update about where we are in the class and just reminders to keep us all up to date. Now I'm going to start with aberrations. Aberrations are errors in the image. So when you have an image that looks fuzzy or has something that isn't right, distorted, that's an aberration. And the first one, and one of the most obvious ones, is chromatic aberration. Chroma means color. So chromatic aberration is where you have a poor focus because of different colors. The fact is that glass or polycarbonate or whatever you make your lens out of, it's a dispersive medium. That means that the speed of light for different colors is different. And so our refraction, our bending of light when we go from one material to another, relates to that index refraction. Remember Snell's law, N1 sine theta 1 equals N2 sine theta 2. So if you have N1 equals 1 and N2 is equal to, let's say, 2, then sine theta 2 is going to be half as big as sine theta 1. So it's going to have a much smaller angle. Whereas if N2 was equal to 1, if they were the same, you'd have no bending at all. So the bigger the difference, the more bending occurs. So if we look at this picture up the top, we can say, aha, the violet light bent the most. So that means the index refraction for violet must be the biggest. And of course, bigger index refraction means slower speed. So that means that the violet must have the slowest speed, and thus it has the most refraction. But that different focal lengths, it gives us pretty things like rainbows. It gives us the pretty rainbowish things we see when we look at light through a prism. But it also makes it so you don't have a really good image if you have just a single lens. So I remember when I was a kid watching football, when they would do a super zoom in to show you the football from the other side of the field, you would clearly see a separation of colors because of that chromatic aberration. But over time, scientists have figured out ways to deal with that. So what we have in the lower picture is what we call a dichromat. Di, of course, means two. It's two lenses made out of different types of glasses. One type or one glass has to have a different way that the speed of light changes with frequency, with color, than the other one does. And using those two different lenses made of different types of glass, if you shape them just right, and this is pretty complicated, then you can make two colors come to a focus at the same place. So in this picture with the dichromat, they have the blue light and the red light coming to a focus at the same place. As you might imagine, with only two lenses, it's really only two colors that you can get to come to a focus at the same place. So for more complicated systems, they might use a trichromat. A trichromat, then you have three lenses that makes it so you can have of dissimilar materials again, that makes it so you can have three different colors all come to focus at the same time. Combined, these things are called achromats. They're things that are designed to get rid of, the A means no, the chromatic aberration. So that's one type of image error and how it's corrected. Now you should know about chromatic aberration, what causes it, how it's corrected. As you can see here, we have no calculations associated with that. Our second image error, our second aberration, is off-axis astigmatism. Now, when we were talking about vision, we saw that astigmatism is the result of an asymmetry of the eyeball. And so we had different focal lengths depending on which orientation the light's coming from. Well, this is a little different. This is an astigmatism, a different focal length problem, but for light that is not parallel. You might remember that we talked about parallel incident rays, and parallel incident rays all come to a focus at one point. But those parallel rays were assumed to be parallel to the principal axis. So off-axis astigmatism is when you have, in this case, parallel rays, but they're not parallel to the principal axis. Perfect. So that's off-axis astigmatism. It's because the focal length essentially is different if you're coming at an angle other than parallel to that principal axis. Another name for off-axis astigmatism is a coma. A coma because you get something that focuses looking like kind of like that. Spherical aberration is one of the most prevalent things we see. When we grind, and I've never ground, of course, but when people grind lenses, they grind the surfaces so that they are part of a sphere. So that's a spherical arc. Why do they do that? It's not because it's the perfect shape, but because it's an easy shape to grind. It's much harder to grind different shapes. The problem is, if you have a lens that's fairly small, then they come to a focus at pretty much the same place. But if it gets bigger, spherical isn't the right shape, and so the focal length from the rays that are hitting the external part of the lens come to a focus at a different location than the rays that are in the interior part. And so then you have a range from the focus in the outer part to the focus in the inner part. And so you have an unclear focus. That's called a spherical aberration. That's one of our big problems in optics because we tend to use spherical lenses and mirrors. You have the same problem with the lenses you have with the mirror here. Now, if we go back, the off-axis astigmatism, same problem with the mirror as a lens. Chromatic aberration, not a problem at all if you use a mirror. Mirrors don't have chromatic aberration because they work based on the law of reflections that says theta incident equals theta reflected. There is no speed of light, no index of refraction calculation here. And so there is no such thing as chromatic aberration for a mirror. But there are these other ones for a mirror. And so for special situations, you might have a special shape. If you have light coming from infinitely far away, that's parallel rays, and you want to focus it on something that is, nearby, then you actually would want parabolic for the shape of your mirror. Parabola. I think it's 1L. If distance object equals infinity, or since light works the same forwards and backwards, if you want distance image equals infinity. So a spotlight, you want distance image to equal infinity. And if you have let's say a satellite dish, then you have distance object is infinity. So either one of those, parabolic is the appropriate shape. If you have distance object is between the focal length and infinity, and likewise distance image is between the focal length and infinity, then you actually use an ellipsoidal shape. Those would be the ideal shapes. But they're hard to come by. When I was in graduate school doing my research for my PhD, I was dealing with light that I needed to focus pretty accurately. And so I actually had an off-axis ellipsoidal mirror so I could take that light and focus it having distance object and distance image not equal to infinity. Okay, so that's enough on aberrations. Let's get into the wave nature of light. Now, what we studied before, so previously, IOUS, boy, that was really good. Previously, we studied the ray nature. That is, we did geometric optics saying that light is a ray. It has a starting point, travels in a straight line until it hits something. But we also learned that light is an electromagnetic wave, EM wave for short. And if it's a wave, then it must behave like a wave. In fact, you might recall I talked about James Clerk Maxwell saying, oh, look, electromagnetic waves have the same speed as light. Hence, electromagnetic waves must be, light waves must be electromagnetic waves. Very poor logic, but Heinrich Hertz went and did experiments, and he tested the behavior of electromagnetic waves and found that they follow the same rules, things we're going to look at here, interference and diffraction, as well as reflection, that light follows. And then he said, okay, so, it walks like a duck, quacks like a duck, it must be a duck. And so now we do believe that light is an electromagnetic wave, but it's because it has these properties that we're going to look into here, the wave nature of light. So if we're talking about waves, we talk about wavelengths and frequencies and whatnot. And a new term for us to learn is coherence. So coherent light is light that has a fixed phase relationship. Now you might be saying, what in the world is a phase relationship? Here's my drawing of a wave. you have crests there and there, and you have troughs there and there. And you define a wavelength, which is the distance to repeat, and we use the symbol lambda for the wavelength. And you have frequency multiplied by wavelength is equal to the wave speed. Those are all things that we've already studied. But we haven't paid a lot of attention to something like phase. So phase is a measurement about when it reaches its peak, when the crest occurs. And if I have two waves, they are said to be in phase if they have the same wavelength and their peaks occur at the same location. So this is in phase. Now I could draw a similar picture. Here's my green wave. Here's my purple wave. These, you notice I have the trough of the green one is where the crest of the purple one is. It's supposed to be the trough of the purple one's the same place I have the crest of the green one. And these we call out of phase. So in phase and out of phase, both of these are examples of coherent light. Coherent because they have a fixed phase relationship. If you take the phase, so I'll give you a strict definition for phase. Phase is an angle between when the first one is at its peak and the next one is at its peak. So if I look at this, you know sine waves, sine of omega t plus theta, I'll put in here. And so this here is an angle, and as time progresses, the angle changes. And so this here represents a difference in angle. And so in this case, the difference in angle from here to here, from peak to minimum, is 180 degrees. So in this case, my phase difference is equal to 180 degrees, or we'll often put it in radians, pi radians. I don't technically have to put a unit with radian because it's unitless. So this is 180 degrees out of phase, or pi radians out of phase, and that's what we call out of phase. This here, the angle between the two, is 0 degrees, or it could be pi radians, or not pi, 2 pi radians, or it could be 4 pi radians, and so on. So if the phase difference is an integer multiple of 2 pi radians, or 360 degrees, that's in phase. If it is an odd integer multiple of 180 degrees, that is 180 times 1, 180 times 3, then it's out of phase. So these are examples that I've done so far that are coherent. They have a fixed phase relationship. So what's incoherent? Well, if you have light that's, here's one wave, and here's another wave, well, those are not coherent. There's no fixed relationship between when the peak is going to be from one and the peak of the next. That's one example. Incoherent is when you don't have a fixed phase relationship between the waves. So if they have a different wavelength or different frequency, they're not going to be coherent. You can also have light that has, here's one wave, and here's another wave, and here's another wave. If they all have the same wavelength, but they have their peaks at kind of randomly dispersed times, they're incoherent. It has to have a fixed phase relationship to be coherent. So here's an example. You have this one's peak is there, that one's there, that one's there, that one's there, that one's there. There's no fixed relationship between the phases, whereas here, they're all peaks together, all troughs together. That has a fixed relationship. So this is a coherent light source. This is incoherent. Now, in reality, nothing is perfectly coherent. Nothing is perfectly incoherent. If you take an incandescent light bulb, you have a piece of tungsten, and you connect it to power supply, and that tungsten gets hot and it gives off light. The light that comes off will have what we call wave trains. It's coherent for a certain distance, but then it flips, it shifts its phase. So you have a short coherence. And so we actually talk about this as a wave train. This is the length of the wave train. And so for an incandescent light bulb, it's a very short wave train. Whereas if you have a laser beam, the laser might be coherent for several kilometers. Its wave train is very long. And in that case, you can do a lot of things utilizing what we call interference if you have that long wave train. So there's an applet here that just shows us what happens when we have two coherent waves and they have a varying phase relationship. So this applet is simply going to shift the phase between the two waves. So I have f of x here has, for some reason my drawing tools aren't here, f of x is a phase of 0 degrees. G of x is going to have this phase of theta, and it's going to change. Now, if they're in phase, this is plus 0 and this is plus 0, notice what happens. You have two different waves that are exactly on top of each other, so you can't see the difference. And the red is the sum of the two. And so the red gets really big up here, indicating that we have what we call constructive interference. Now, if I start this, now the phase is changing. So now you can see the two waves, and you see that the amplitude is getting much smaller. You have much smaller constructive. And in fact, if we get right here, okay, I stopped 2 degrees off, but that's good enough. You have destructive interference. You have the blue wave, you have the green wave, but you add them together and you just have a flat line. You have nothing. It completely destroyed it. It's like you have no wave. And then, of course, you keep going, you get past 180 degrees, and you start to have constructive interference again. So this is just illustrating the difference in constructive and destructive interference. This is used in many devices, and here's an example. Much better than the example of the radar gun that they used to give you speeding tickets. The Michelson Interferometer. The Michelson Interferometer is using the interference between one wave and a different coherent wave to make a determination about distance. So the basic design is you have a coherent light source. So this is showing it with a laser. Very often we show red lasers because ruby lasers are very common. The helium neon laser, HENI for short, is very common. Both of those give you a nice red color. Now the light from this laser comes out to a glass that is 50% reflecting. So you have half of the beam that comes through, half of the beam gets reflected out that way. So the beam is split on this, hence it's called S for beam splitter. Light hits this mirror, comes back, and of course, if it's a 50% reflecting mirror, then this is going to be 1/2 of the original intensity, and this is going to be 1/2 of the original intensity. They come over here. I'm going to use different colors because I should. When the light that came on path D1 comes to this mirror, 1/2 of that 1/2 I0 is going to be reflected. So this is going to be 1/4 I0. And the light that went along path 2, when it comes back, half of that 1/2 will be reflected. So that's going to be 1/4 I0. So we have 1/4 I0 for one path and 1/4 I0 for the other path. But now they're back together, and this light started in phase. So originally, we had the light was perfectly in phase. because of these two different paths, the light could now be a different phase because one path might be longer than the other. If the path is longer, there's more wavelengths in it, and so the phase has shifted. And so what we look for here is, you see it has light and dark fringes. The reason for the circles is because of geometry. If you were going up, then you have a different pathway. But we look here and we look for changes in the constructive and destructive interference. You can see it's constructive where you have bright light. So in this picture in the center, it's constructive, and then you have destructive every time you have a dark band. And we call those fringes. You have maximum intensity as a bright fringe, and you have no intensity as a dark fringe. So let's look at a problem that uses this interferometer to see how it works. So we have a transparent vessel with a cavity 30 centimeters long that's placed in one arm. So let's say we put that cavity right here. So now the light is going to go through that cavity if it goes through D1, but not if it goes through D2. And we look at our picture initially before we put anything in that vessel, and we say, okay, now we have our initial viewing. We have light in that in vacuum has a wavelength of 633 nanometers. So I'm going to put lambda sub 0 is equal to 633 nanometers. And the air is removed from that vessel. So we pump it out so it is a vacuum. And as we go through that pump, we see these fringes start to move. And we count how many new fringes were created. We see that there were 274 bright fringes that occurred in pumping out the air. And now we have a question that probably to you seems ridiculously unrelated to anything we've done. Calculate the index of refraction of air. Well, we need to think about how we can approach this. So the basis of the Michelson Interferometer is that we can measure how much the light has gone into and out of phase. So if we have n equals 274 fringes, then that means that our change in phase is that's the phase of one versus the phase of the other, is 274 times 2 pi radians. That seems rather non-helpful, but we can also talk about the change in path is equal to 274 wavelengths. Now, did our path length change? No. Those are two different ways of writing the same thing, and it seems kind of wrong in both cases. But here's what we know. We know that the wavelength in air is equal to the wavelength in vacuum. Oh, boy. Yeah. The wavelength in vacuum divided by the index refraction of air. And the wavelength, well, yeah, that's that. And we know that we went through 274 wavelength change in that vessel. So the number of wavelengths, I'll put N1, the number of wavelengths that fit in the vessel when it had air in it, actually I guess I should put N air, is equal to the number in vacuum plus that N of 274. How did I get that equation? I know that the wavelength in air is shorter than the wavelength in vacuum, right? Because N is always bigger than 1. So if N is bigger than 1, then lambda air has to be smaller than lambda 0. So since the wavelength in air is shorter and the length of that chamber is fixed, then I'm going to have had more wavelengths that fit in there. So now I say, well, how do I calculate how many wavelengths are in there to begin with? So I'm going to have the number of wavelengths in air is equal to, well, let's do this a different way. No, I'm going to do it this way. The number of wavelengths in air is equal to the length of that chamber. They gave us the length of the chamber is 30.0 centimeters. I'm going to convert that into nanometers. 30.0 times 10 to the 7th nanometers, times 10 to the 7th, because nanometer is 10 to the minus 9 and centimeter is 10 to the minus 2. So it's going to be the length divided by the wavelength in air. But we know that the wavelength in air is the wavelength in vacuum divided by its refraction error. So invert and multiply rule. So that's the number of wavelengths we have in the air. Now, the number of wavelengths in vacuum is equal to the length of that chamber divided by wavelength 0. Well, we know these numbers. We know L and wavelength 0. So I'm going to actually calculate that right now. Well, yeah, I'm not going to calculate now. I'll calculate in just a moment. So if I put these together, put N vacuum in there and air in there, I'm going to have L over lambda 0 times N in air equals L over lambda 0 plus N, that N of 274 fringes. So solving for N air, that's what I need to calculate. So 1 plus 274 times 633 nanometers. Oh, winning. Now you see why I changed to nanometers, because those units are going to cancel each other out. And now I just have to calculate that number. And oddly enough, I did not calculate that number before starting this lecture. So I'm just going to use my handy dandy Google to calculate it on a different computer here. 1 plus 274 times 633 divided by, I hit the wrong button. Divided by 30, 1, 2, 3, 4, 5, 6, 7. And that gives me 1.00058. Actually, I should have one more decimal place, 578. You might ask, why do I have one more decimal point? Because I have 3 significant digits in that calculation and an infinite number in the cardinal number 1. So I have, these are the 3 significant digits. My total answer, of course, here has 7 significant digits. That's the way significant digits work. So we're able to use this Michelson Interferometer in a basic measurement to determine what the index refraction of air is. Kind of cool. Now here's something really cool. Thin films. You probably have noticed you blow a bubble, and in that soap bubble you see pretty, pretty colors. Well, this is just an example of that. Here you have a bubble on this wire, and because of the orientation, gravity makes it so down here you have a thicker film, and up here you have a thinner film. And you see pretty separations of colors as you go down. And of course, this is physics. We look at this and we say, why? And as you could gather from the topic of the day, it must have something to do with interference. It must be light interfering with other light. But what is fundamentally going on? Well, you have a thin film and you have the incident ray. Now, in these pictures, we draw the incident ray so it's coming at an angle to the surface. But for calculational purposes, we assume this angle is approximately equal to 0 degrees. That is, it's basically coming in normal. We draw it at this angle so we can differentiate the light passing through versus reflected. So looking at this picture, we have that light that comes in, and we have some light that gets reflected. The light that gets reflected is around 4%. And we have some that's transmitted, that's around 96%. And then it hits this surface, and we're going to have the amount that's transmitted is about 0.96 times 96%. And the amount that's reflected is about 0.04 times 96%. And then the amount that's transmitted out here is about 0.96 times 0.04 times 96%. Right, 4% reflected at each surface, which means the transmitted is the remaining 96%. So this reflected light here is going to be 0.04 squared times 96%. And then this transmitted is going to be 0.04 squared times 0.96 times 96%. And you can go on and calculate the rest of them. But here's what's important. 4%, 0.96 times 0.04 times 96%. How big do you suppose that is? Well, I'll tell you. 96 times 0.04 times 0.96 is 3.69%. 3.69% is pretty close to 4%. So the intensity of reflected ray 1 and reflected ray 2, that's very similar. Now, if we look over here at the transmitted rays, obviously there is a big separation in the intensities here. So you have a much weaker interference that can occur between rays A and B on the transmitted side compared to the reflected side. So we often just focus on the reflected side because that's the side where you have a very noticeable relationship because they're similar intensities. That's why in this picture, we are looking at the reflected light. So to go further in analyzing what's going on up here, we have to answer a couple questions. So thinking back to things we learned first semester, what happens to a transverse wave when it is transmitted from a slower to a faster wave speed string? So that's like I have slower strings, the speed depended on the mass per unit length. So I make a big thick one there, and then I have a little one there. And so this is slower. This is faster. And what happens to a transverse wave when it goes from left to right in this picture? Obviously, we're not in a classroom setting, so I can't get your feedback, but I want you to think through these, and I will go through each one. Is the answer nothing? No, the answer is not nothing, or probably I wouldn't have asked the question. The transmitted wavelength is shorter. Well, we know, I'm going to come down to these first. Transmitted frequency increases or decreases? Neither. We know that the frequency must remain constant. If the frequency didn't remain constant, the left side here would be going up and down at a different rate than the right side, and the two wouldn't be tied together. So the frequency has to remain constant. It's just not possible to have continuity of a wave and have a changing frequency. So the frequency has to stay constant. But since Well, what I wrote earlier today was frequency times wavelength is equal to the wave speed. Then we must have the wavelength is equal to the wave speed divided by the frequency. So if the wave speed is faster and the frequency stays the same, then the wavelength, wait, did I do math right? Yeah. So the frequency times wavelength, yeah. So if the frequency goes up, the wavelength goes down, but the frequency is staying the same. If the wave speed increases, then the wavelength increases for the same frequency. So the wavelength has to be lengthened because the frequency had to stay the same. Now we have one more option here. The transmitted wave has a phase inversion. What does a phase inversion means? That means that instead of going as I showed in the picture, it would be going something like this, right? It's reversed, just the opposite. And that does not happen ever with transmitted. Aha, not ever with transmitted. So let's ask its partner question. What happens to a transverse wave that is reflected from a string with a faster wave speed? So it's the same idea. That is, I have the fatter string, and then it goes to a smaller string. So it's faster here, slower there. And it's asking about the reflected wave. Well, think about it like this. You have a light string here. That light string, it really isn't doing much to affect the heavy string. So the heavy string just does what it wants. And so it's going to have, of course, the same wave speed. If it has the same frequency, they always have to have the same frequency. If it has the same wave speed, if the frequency is the same, the wave speed is the same because it's staying in the same string, then the wavelength can't change either. So the wavelength didn't change, the frequency didn't change. What about the phase inversion? This thing here doesn't really affect it. So really no phase anything. You have if this end was going up, there's nothing stopping it. It just wants to keep going up and it pulls the string up with it. And so the reflected wave has no change. Final question. Whoops, didn't ask the final question. What about if I reversed it? What if I had the wave coming on the fast string and then it went to the heavy string? Well, the reflected wave is now pushing on something really heavy. If this is going up, that's restricting its going up and makes a wave that is pulling down. And so it causes a phase inversion for reflection from a faster off of a slower. So this would have a 180-degree phase shift. So there really were 3 questions I should have asked, and I only asked 2 of them. Here's pictures to illustrate what I mean. So instead of showing a continuous wave, we just show a pulse. The pulse is much easier to analyze. So here I have a wave coming in a faster medium, the smaller string, hitting the slower medium. When that wave is hitting here, the wave pulls up, but this heavier string, because of its inertia, pulls down and makes the reversed reflection. But the transmitted wave is still the same phase. It had no shift. If I reverse this situation, the slower medium comes in. When it gets here, the string is pulling up and it's getting no resistance, so it just keeps going up and makes the reflected wave the same orientation, same phase as the incoming wave was. In all cases, the transmitted wave had no phase shift. And you'll notice the width here became larger on the transmitted wave in the faster medium because it had a higher wave speed. The wavelength here became shorter, and of course, pulse width is what we use as a proxy for wavelength because of the slower wave speed. So now we can apply that same rule to light. So if I have light that's in a faster medium, which means a lower index refraction, when it hits the barrier, the slower medium, higher index refraction, is like the heavy rope, and it's going to cause a 180-degree phase inversion. That's kind of redundant. It's a 180-degree phase shift or an inversion on the reflected wave. But if I reverse that, if it's coming in the slower medium and reflects off, the transmitted has no phase shift, or excuse me, the reflected has no phase shift. So that's a rule that we have to apply in analyzing what's going on here with our thin film. So let's now do the analysis. So if I have this light coming in, what I'm going to do is I'm going to calculate the phase for each of the first two reflected rays, as well as each of the first two transmitted rays. So the first ray, it's going from N1 is equal to 1.00, or N incident. N of the film, if it's water, that's 1.33, and then N transmitted back to air, 1.00. So here we have the incident rays reflecting off of something with a higher index refraction. Higher index refraction means slower wave speed, means that the reflected ray has a 180-degree phase shift. So my phase for ray 1 is 180 degrees. Now, the light that comes through here, transmitted, never has a phase shift, but it has to go a distance t and then back a distance t to get to ray 2. So that means I'm going to have phase 2 has, first of all, 2 thickness divided by the wavelength. Oh, it's not in air. It's the wavelength in the film. But using the equation that we used previously, the wavelength in the film is equal to the wavelength in air, I'll put wavelength 0, divided by index of refraction of the film. So I'm going to substitute that in here, but I have one more thing I have to look at before I substitute it. The other thing I have to look at is the reflection. Is there a phase shift if I go from 1.33 to 1? Going from a higher index to a lower index means you're going from a lower speed to a higher speed. If you reflect off of a higher speed material, there is no phase inversion. So I'm just going to have plus 0. And now if I substitute the equation in red above, this is equal to 2 thickness over wavelength in vacuum or air. Remember, we treat them as the same thing, times the index of refraction of my film. Is that constructive or destructive? Well, the phase difference between the two, remember, this is the same incident ray of light, so there was no phase difference initially. So the phase difference between the two is phi2 minus phi1. So that's going to be, oh, I forgot one more really important thing. I'd better multiply this. First, I'm going to change to radians, equals pi radians. And this, I need to multiply by 2 pi radians because there's 2 pi radians in a cycle. So now my phase difference is going to be 2 thickness NF over lambda 0 times 2 pi radians minus, where am I? Oh, I shifted down, minus pi radians. So my total difference here is 2 thickness and lambda 0 times 2 pi rad minus pi rad. That's my phase difference. Now, how do I know if it's going to be constructive or destructive? Well, constructive interference, we learned, if the phase difference is equal to an integer multiple, so I'll use m as an integer, of 2 pi. And it's destructive interference if the phase difference is equal to m plus 1, or 2m plus 1, excuse me, 2m plus 1 pi radians. Why 2m plus 1? Because if m is an integer, then if m is equal to 0, that would be pi. If m is equal to 1, that would be 3 pi. If m is equal to 2, it would be 5 pi. It's odd multiples of pi radians. So we can look up here and say, aha, if I want constructive interference, I'm going to have m times 2 pi radians equals 2 thickness n film over lambda 0 times 2 pi minus pi. We'll divide everything by pi, just to make life simpler. There, I divide everything by pi. I have 2m. Well, let's divide everything by 2 pi. There, divide all, so I don't have the 2 there. M is equal to 2 thickness nf over lambda 0 minus 1/2. So if m is equal to 0, that would require a certain index of refraction. If m is equal to 1, it'd be a different index of refraction. We can calculate what wavelengths, that's what we usually do, the wavelengths for constructive interference. It just solve that for lambda 0. So I'd have, well, let's do the work first. M plus 1/2 is equal to 2 thickness nf over lambda 0. So now if I solve for lambda 0 for constructive interference, that's going to be 2 thickness n of the film over m plus 1/2. So that's the wavelengths that will give me constructive interference. What if I want to know about destructive interference? Well, for destructive interference, I just use the red relationship there of 2m plus 1 times pi rads. So I actually broke this up. I used 1.5. I should use 1.33 because it was supposed to be a water film. If I wanted destructive interference, I would have the phase difference is equal to 2m plus 1 times pi is equal to the relationship that we had already calculated here for the phase difference. So the phase difference equation is there. So that's 2 thickness n of the film over lambda 0 minus pi. I think that's right. We got to look back just to make sure. Oh, times 2 pi. I forgot the times 2 pi in the first one. Times 2 pi minus pi. So once again, let's cancel the pi's right off the bat. And that gives me 2m plus 1 is equal to 2 thickness times 2 over lambda 0 minus 1. Well, let's go ahead and add 1 to both sides. 2m plus 2 equals 2 thickness n final times 2 over lambda 0. And this is destructive now. So if I want to find the destructive wavelength, lambda destructive, notice cancel a 2 from every term, don't try to cancel 2 times 2. 2 thickness and final over m plus 1. So there's the destructive relationship. Here was the constructive relationship. M plus 1/2, m plus 1. Now, what are the values for m? M is any positive or negative integer. So m plus 1, since 1 is an integer, m plus 1 could just as well be m. So you might put lambda 0 destructive is equal to 2 thickness and final over m prime, where m prime is equal to m plus 1 is any integer. And you have a relationship for the destructive wavelengths here and the constructive, Control Z for that, interference here. Well, I only looked at 2 cases. I looked at reflected constructive interference and reflected destructive interference. I could have also done transmitted constructive and transmitted destructive. If I look at the transmitted rays, I'm going to come all the way up to here. Actually, now let's just go. I've got this picture. If I look at the transmitted rays, I'm going to have phi A is equal to, it had to go through a thickness here. I'm not going to count that, and I'm just going to say 0. I'm going to use, please don't have closed it. No, it's there. So I'm just going to use A as my reference, and I called that 0. And then I have a reflection here, reflection from 1.33 to 1. So no phase inversion on that reflection. Goes 2 thicknesses. What about this? From 1.33 to 0, no phase inversion there. So there's no phase inversion on either of the 2 reflections. So phi B is equal to 2 thickness times n film over lambda 0. Just as we found, sorry, that's my arm hitting the space bar apparently. So here I have my relationship between the phases of A and B. And so I can use the same for constructive. Oh, I forgot the 2 pi yet again. For constructive, delta phi is equal to some integer times 2 pi radians. And based on my relationship here, that's going to be phi B minus phi A, which is 2 thickness n film over lambda 0 all times 2 pi. So just cancel the 2 pi's from each one. Oh, minus 0. Cancel the 2 pi's from each one, and you have m equals 2 thickness n final over lambda 0 constructive. So lambda constructive is equal to 2 thickness n of the film over m, where m is any integer. Now, I say any integer, but remember, when you put it in this way, any integer works, but you can't have a negative wavelength, so it's going to have to be a positive integer. And if I wanted destructive, the final thing for destructive would be change this m2 pi to 2m plus 1 multiplied by pi, and you're going to get m plus 1/2 on the bottom. So there's 4 equations total here. One for constructive reflection, one for destructive reflection, one for constructive transmission, one for destructive transmission. On the exam, I'm not going to give you those equations. What I will give you is these relationships in some form. That is, if the phase difference, if it's constructive, then the phase difference has to be some integer multiple of 2 pi radians, or if it's destructive, it has to be some odd integer multiple of pi radians. And I will leave it to you to figure out is this going to be a constructive or destructive situation? Now, let's look at a problem so we can make sure we can do this. Oh, here's the things you need to do to analyze the problem then. Just like what we did, depending on the indices of refraction of the three media, you could sometimes have a situation where you have something like air, water, glass. In that case, you have N1 equals 1.00, N2 equals 1.33, N3 equals 1.52. And you have to analyze, is a reflected ray going to have constructive or destructive, or excuse me, phase inversion or no phase inversion? And of course, if you're going from air, it's a slower medium, so you have a phase inversion when you reflect off the water. If you're going from the water on glass, there's also a phase inversion because it's hitting a slower medium. So both the reflections coming out from air would have phase inversions. So you have to pay attention to what you're given. So that would give you another set of four equations if you have this order of indices of refraction instead of lower, larger, lower. If the index refraction of the film, yeah, we already have that. Yeah, these are just the things to pay attention to if you're going to have phase inversions on the reflections, and then calculate the phase difference between two reflected or two transmitted rays to determine if it's constructive or destructive. So notice drawing a picture, even if the problem concerns normal incidence, because we always do, draw the incident ray with a non-zero angle of incidence to separate the rays and label the indices of refraction. You want to make sure that's out there. Then decide, I don't know what that came from, decide whether you have a phase inversion or not for each reflection. Find, I said here, the path length difference between the two rays, the way I did it today. That is one way I do it. But here I just did the phase difference. So I just did the phase difference directly. And then calculate the overall phase difference. That's the phase change from 1 to 2 or from A to B. And compare to the situation you're looking for, constructive or destructive. Now, back to the original picture. We have soapy water, and the index refraction for the film is 1.36. So we're saying it's the same index refraction for all colors in this case. We're looking at reflected light. So that's going to be the first two cases we did for constructive and destructive. In fact, let's just go back up there and review. We have for constructive interference, we're going to have, yeah, this was the first one. For constructive interference, we have 2 thickness N film over M plus 1/2 is constructive. And for destructive, we will have 2 thickness N film over M plus 1. So I'm going to write that here. Theta constructive on reflection, in this case, 2 thickness N film over M plus 1/2, and theta for destructive, 2 thickness N film over M plus 1. I am sorry, my confidence. I just have to go make sure I did that right. So I've written down what we know that we can apply here. And now we're going to explain why the film appears black at the top. Was it constructive or destructive interference if it's black? Must be destructive. Constructive, we'd see something, right? And so you might try to use this equation and say, aha, we have destructive interference. So, but that gives you, in this case, M is an integer, T is the thickness. And I told you at the outset of this lecture, or not but the outset of this section, that it's thin here and thick here. What's changing is the thickness. And so up here where it's thin, we must be in a situation where the wavelengths that are giving us constructive interference, short thickness, small wavelength. So only UV, ultraviolet light, that's short wavelength, has constructive interference until we get to a certain threshold thickness, right? We see lambda minimum is around 400 nanometers, which means that for m equals 0, is 2 times thickness times n of my film 1.36 divided by 0 plus 1/2 equals 4 times 1.36. That's I'm going to calculate it. 4 times 1.36, 5.44. Times the thickness. So if my thickness is less than 400 nanometers over 5.44, which is 73.5 nanometers. Now that's pretty thin, right? If my thickness is less than 73.5 nanometers, I'm not going to have any constructive interference possible. So I have black because I have no constructive interference occurring. So that's why it's black at the top. It's too thin. Now, the light reflected perpendicular to film at a certain point. So this is a certain point. That means a certain T is missing the wavelengths 504 nanometers and 630 nanometers. No wavelengths between these two are missing. So I can come here to the destructive interference because it's missing, and I have lambda m is equal to, and notice as m goes up, the wavelength goes down. So when my m is the lowest value, it's going to be 630 nanometers. Is equal to 2 thickness and film over m plus 1. And lambda m plus 1 is equal to 504.0 nanometers equals 2 thickness and final over, instead of m, I now have m plus 1 plus 1. So that's m plus 2, if you will. And now I want to try to calculate what the thickness is. So I have or lambda m. Well, let's go down to the next line or next page. I gave myself room. Lambda m minus lambda m plus 1. Yeah, that looks like a, no, it's not the best way. I am actually going to first calculate the m. Lambda m over lambda m plus 1 is equal to 2 thickness and final over m plus 1 divided by 2 thickness, not final, and film over m plus 2 equals m plus 2 over m plus 1. So if I cross multiply, I would have lambda m times m plus 1 equals lambda m plus 1 times m plus 2. That plus sign did not come out looking right. And so m times lambda m minus lambda m plus 1 equals 2 lambda m plus 1 minus m. So m is equal to 2 lambda m plus 1 minus lambda m over lambda m minus lambda m plus 1. Lambda m plus 1 was my 504. I'm not going to have space to write it there. And the other one was 630. And so let's just calculate that number. That's going to be 2 times 504 minus 630. It's 378 on top. And on bottom, that's going to be 126. And that gives me exactly 3. So now that I know m is equal to 3, I could use either of those original equations. Let's just use lambda m is equal to 2 thickness index refraction of the film over m plus 1. So didn't need to do that. Thickness. Let's change colors. I'm tired of purple. Thickness is equal to lambda m times m plus 1 over 2 end of the film. So that's 630.0 nanometers times 3 plus 1 all over 2 times 1.36. And that gives me, for my final unsophisticated answer, assuming I made no mistakes, 926.5 nanometers. And actually, that was only 3 sig figs, cardinal numbers there and there, 4 sig figs. So my answer has 3 sig figs. That would be 927 nanometers. So we found the thickness for that specific location. What other visible wavelengths are missing, if any? Well, what is the visible wavelength? Visible wavelengths are 400 nanometers to 750 nanometers, roughly. Those are rough numbers. Depends on who cuts off where, and that's where I cut off. And so we would just go through and we'd say, okay, what other, I have this thickness of 927 nanometers, 2 times 927 nanometers times 1.36 divided by what gives me and so we've already looked at 3, we've looked at 4, right? This was 3, this was 4. And so I might try 2 and I might try 5 and see if there's another missing one in the visible spectrum. I'm not going to do that calculation. Now, the history of light being a wave, light being a particle, Young, Sir Thomas Young, came up with a really novel thing to show that light had to be a wave. People had argued, is light a wave or a particle? Newton said, oh, light is a particle, and he had lots of explanations. But then Thomas Young came along and he said, no, light has to be a wave. And the reason is because of the double slit interference. So if you have coherent light, so how he made coherent light was a single slit here. Let's not worry about how he made coherent light. If you have coherent light and it goes through 2 slits, what happens? Let's imagine that we have particles, like we're throwing baseballs, and I have 2 slits in a wall. So baseballs can go through these 2 slits. And then behind there, what am I going to find for where the balls land? Well, if you look behind there, so here's looking at, there's one gap. Here's the other gap. If I'm throwing balls, I'm going to find a bunch of balls around here and a bunch of balls around here. That's it. That's not what happens when you have light go through those slits. Instead, when you have light go through those slits, what you find is that you have the most light right in the center between them, and then it trails off and comes up, and you have a whole bunch of places where it's light and dark. And this is a demonstration I would have shown you in class. We can physically see this. It's very nifty. And you're like, well, that makes no sense. That's not what happens when you throw balls through a slit. And Thomas Young would say, exactly. That's because you're not throwing particles through the slit. You're sending waves through. And so those waves, according to Huygens' principle, those waves, each point on a wavefront acts as a new point source. And so the waves come out, and then you're going to have a path from here to here and from here to here. Those are different lengths, which means that you've gone through a different number of wavelengths to go from point A to point B as compared to from point C to point B. Since you've gone through a different number of wavelengths, the light that was in phase at these two slits is no longer in phase. One had a longer path than the other. And so here you had, well, at the center, just geometrically, if you're at the center, you had to have a phase difference of 0. And here you must have had a phase difference of pi, and here a phase difference of 2 pi, and so on. And so we can give a wave explanation for this, but there is no particle explanation. I've already shown you the graphic on constructive and destructive interference, but here I have a little math. If you have small intensity waves, when you have two waves hit the same place, the amplitude is just added together. Well, the displacement is added together. And if these are two coherent waves that are in phase meaning phase difference is 0, then we can replace the displacements with the amplitude. And the amplitude of what results is just amplitude of the first one plus the amplitude of the second one. Well, the intensity of light is proportional to the amplitude squared. So that's why I have intensity is C times A squared. Intensity of 1 was C times A1 squared. Intensity of 2 was C times A2 squared. C is just a constant. So the intensity of the combined light is equal to, C times A1 plus A2 quantity squared. Well, if you square this, you have A1 squared plus A2 squared plus 2A1A2. And so the intensity, this here is intensity 1, this here is intensity 2, and if I take square root of C times A1 multiplied by square root of C times A2, that's square root of intensity 1 times square root of intensity 2. And so the intensity that we get is bigger than the sum of the two intensities. It's intensity 1 plus intensity 2 plus 2 times the square root of intensity 1 times intensity 2. Kind of cool. Well, what if it's destructive interference? If it's destructive interference, then the amplitude is the difference between the two. So I would have A1 minus A2 here, which is going to change the sign right there. So if they're out of phase, then you're going to have the intensity is equal to intensity 1 plus intensity 2 minus 2 times square root of intensity 1, intensity 2. Now you notice if intensity 1 equals intensity 2, then this would equal intensity 1 plus intensity 2 minus 2 intensity 1, or intensity 2. I'll just put intensity 1 for all of them if they're equal, and that would be equal to 0. So if the intensities of the two waves are the same, then the intensity of the destructive interference is 0. And likewise, up here, if intensity 1 was equal to intensity 2, then this would have been twice the intensity. here's a picture for us to think about coherence and constructive and destructive interference. So here I have two speakers, and this lady is sitting here listening to the speakers at this location. And my first question is, are the two sources, that is source 1 and source 2, are they coherent? I know you're thinking it through. Give you a little time. The answer. Coherent means a fixed phase relationship. Well, if I look at the speakers, at the speaker at the same time, they are exactly in phase. And so there's a fixed phase relationship at the speaker. At this lady, they are a fixed phase relationship, but they're 180 degrees out of phase. But in both cases, in both locations, it was a fixed relationship. So the answer is yes, we have a fixed relationship between the phases of the waves. Question 2, how does the sound interfere here? Is it constructive interference, destructive interference? Is it constructive part of the time, or do I just not have enough information? Right, constructive part of the time means also destructive part of the time. Well, if you look at this picture, right now it's definitely destructive. And because we have a fixed phase relationship, it's always going to be that 180 degrees. So it's always destructive for her because it's coherent and destructive. Already gone. Well, remember when I talked about phase difference, I did the difference in phase is equal to like 2 pi times m for constructive, right? Well, if I talk about a traveling wave, the distance it travels is equal to a wavelength for every 2 pi radians. So for constructive, that's going to be the wavelength times 2 pi m over 2 pi is equal to lambda m. So it's going to be an integer number of wavelength differences for the path length for constructive interference. And likewise, if I want destructive interference, if I go through the same thing, my path length difference is going to be lambda over 2 pi times 2m plus 1 parentheses, yep. Cancel that pi, and I have equals lambda times 2m over 2 plus 1/2, or of course that's m plus 1/2. So there's our relationship for constructive versus destructive interference if I talk about just the difference in path length. And if you go back to that thin film calculation, we actually did that. We calculated the phase difference as the light traveled through the film looking at the path length. So we have destructive and constructive. Oh. So in cases where the two paths are not completely in the same medium, you have to keep track of the number of cycles in each medium separately, which is what we did in our calculation with that Michelson Interferometer, where it went into the vessel and we pulled out the air, so the index refraction became different, and we had to take that into account. So let's look at a simple one medium problem. A microwave transmitter, that's the T marked here, and a receiver, the R, are set up side by side, and there's two flat plates. They're going to reflect the waves. So we have a distance d from the transmitter to a fixed reflecting metal plate. And then the second plate is going to move out some distance x from d. So the length for path 1 is 2d. It comes out d and comes back d. I know the picture shows them offset, but we're assuming the offset is so small as to be insignificant. So length 1 is 2d, but length 2 goes out d plus x, comes back d plus x, and so it has a length of 2d plus x, or 2d plus 2x. So the path length difference, delta L, if you do the work, you put in L2, 2d plus 2x, that's L2, minus L1, 2d, is 2x. So path length difference is 2x. Now, constructive interference versus destructive interference. We're going to look at experimental result. Experimental result says that when x is equal to this value, it's constructive. This value is destructive, this value is constructive, this value is destructive, this value is constructive. So the question is, approximately what is the wavelength of the microwaves? Well, as with all physics problems, it may seem that this is somewhere out there in the blue. I mean, they didn't give you anything specific on how to solve this, but we know that delta L is equal to 2x, and separately from this graph, we know that if I go from this distance, I'm going to have, some integer number of wavelengths because it's constructive. So constructive has delta L is equal to m wavelengths. And so I can write there my equation where, do I know what m is? No, I don't know what m is, but I know that that has to be the relationship. And so I can use this then to once again solve for what the wavelength is. So what is my delta L here? That's about, let's say 3.9, or excuse me, that's x. That's x. X equals 3.9 here for constructive. Here for constructive, that's about 5.2. And here for constructive, I'm going to say 6.5. I put a little before, but it's about 6.5. Right? My significant figures here just to 0.1. So if I look at this, I can say, I have, so I'm going to call this x1, x2, x3. I have 2x1 is equal to m lambda. And I have 2x3 is equal to m plus 2 lambda equals m lambda plus 2 lambda. Well, this is pretty simple. All I have to do is subtract those two. So I'll have 2x3 minus 2x1 equals, and if I take the x3, that's going to be m lambda plus 2 lambda minus m lambda. M lambda, those subtract out, and I'm going to have 2 times x3 minus x1 equals 2 lambda. So lambda is equal to x3 minus x1 equals 6.5 centimeters minus 3.9 centimeters equals 2.6 centimeters. So we get the wavelength, right? The work itself was pretty simple, but we had to think through now what's going on. That's where the physics is identifying what's going on. What can I apply from the things we know? practical examples of interference. Here's how a CD works. A CD, a compact disc, has an acrylic layer with polycarbonate on top of it. The acrylic layer has there's a reflective surface beyond there. And so when the light shines and it will go a different distance in the polycarbonate. And if it goes a different distance, it's going to have a different number of wavelengths that it had to travel. And so what the CD player does is it shines a laser beam on here and it measures the phase shift between what was sent and what is received. And when it goes from a pit to a, what do they call it? A landing? I remember what it's called for the other ones. When it goes from a pit to a landing, it has a different phase shift, and thus it says, it's a 0 or a 1, depending on the phase shift. So that's how we read stuff off of our CDs, just using this destructive interference idea. Now back to Young. There is math involved with Young's double slit experiment. It's not just there's constructive and destructive interference. And notice when we look at these pictures, the constructive interference is falling along each of the solid lines. And so there's an angle here, an angle here, an angle here. And so we usually talk about the angle associated with constructive interference. We have 0 for the central bright fringe, 1 for the one that's off to one side, -1 for the other. Does it make a difference which side's -1 and which side's +1? Nope. It's completely symmetric. It's just a choice of what we consider a positive angle versus a negative angle. And of course, you notice that the intensities vary with position. You can always talk to David Chapman. We'll talk about this on Tuesday and how we get those. So geometrically, how do we determine what those angles are going to be? First, just some labeling. Of course, we have a plane wave coming in with a wavelength lambda. We put the screen some distance, capital D, away from my slits. The slits I'm going to have separated by some distance, lowercase d. And then the position to, let's say, a constructive interference, we're going to call X on the screen. So that's just labeling. And I can make a real quick equation. If I want to relate capital D and X, I would be relating the opposite side of a triangle and the adjacent side. So I'd have tangent of theta is equal to opposite over adjacent. And so I can relate those. Now that doesn't tell me what angles I'm going to have constructive interference. It's just relating the angle with the position. So here's how we solve Young's double slit experiment. First of all, we do what we call far field. And I think the far field is the Fraunhofer. I didn't look this up beforehand. There's Fresnel and Fraunhofer diffraction. I think the far field is Fraunhofer. But what far field means is that D, the distance between the screen and the slits, is much, much greater than the separation between the slits. And if that's the case, theta is very small. So for this case, theta is actually not theta is very small. I didn't do that right. For this case, the angle from slit 1 to screen is the same as angle from slit 2 to screen. That's to a given point on the screen. The angle here, let's call this L, let's call it alpha, is the same as the angle here. That's what the approximation is saying. So if those angles, clearly in my picture, they're not the same. But in our approximation, that angle is the same. This angle alpha then is approximately 0. I shouldn't have called that alpha because that was alpha. So that's our far field approximation. So in that approximation, these two lines are parallel. And if they're parallel, we cut them off at the base perpendicular to those lines. And so this angle theta, the same angle we had right here, that angle theta can be calculated just geometrically. I have the separation between slits, lowercase d. This here is the path length difference. Path length difference because they're two parallel lines going to the same point. It's the same distance for each of them. Even if they weren't perfectly parallel, it'd be the same distance because we've cut it off to make an isosceles triangle. So my delta L is the opposite side. The hypotenuse is D. And so that means that I have a relationship between the path length and the hypotenuse that is, well, that is shown here. You have delta L over D is equal to sine theta. That's our straight geometry, which gives us delta L is equal to D sine theta, which is just what's written in the picture. But remember, for constructive interference, constructive delta L is equal to m lambda, or yeah. So we're just going to put equals m lambda for constructive. But if we want a destructive, delta L is equal to m plus 1/2 lambda. So d sine theta equals m plus 1/2 lambda for destructive. Well, that's actually real simple, right? That wasn't very hard as long as you say, ah, yes, we're using the far field, which has this certain approximation. So there's our equations where m we call the order, and m is an integer, positive or negative. This is just a picture to show you an analogy. If you have two places where you have water droplets hit, you can see that you have constructive interference certain places, destructive interference others. This is destructive. Easier to pick out the destructive than the constructive. So let's look at a problem. A laser with a wavelength of 690 nanometers is used to illuminate two parallel slits on a screen that is 3.30 meters away from the slits. Interference fringes are observed. The difference between adjacent bright fringes in the center of this pattern is 1.80 centimeters. So the center is m equals 0. So that's the center. And then between that and the next adjacent one is here. So that gives me x1 is equal to 1.80 centimeters. And using our geometry as before, x1 is equal to d tangent theta 1. Then it asks, what's the distance between the slits? Well, how would a person calculate that? We know that for constructive interference, this was constructive. We have m sine theta, or d sine theta, m is equal to m lambda. So my d is what I'm looking for. M lambda, well, let's just do it. D is equal to m lambda over sine theta m. M is 1. What is theta m? Well, tangent theta is equal to x1 over capital D. And so if I want to be technically correct, I will actually calculate this value using inverse tangent. And then I'll put that in here. But I don't want to be technically correct today. I want to just be correct. Clearly, 3.3 meters away and 0.0180 meters is this distance. This is a really small angle. And so small angle approximation you always need to check to see if it's really a small angle before you do this. Small angle approximation, sine theta is approximately equal to tangent theta is approximately equal to theta. So I am simply going to put in tangent theta for sine theta. Now this is really simple. Just put in our numbers, 3.30 meters times 6.900 times 10 to the minus 7 meters divided by, oh boy, divided by, no, I did it right. I was looking at the wrong equation. 0.0180 meters. I put everything in meters, so my answer will be in meters. 3.3 times 4, 5, 6, 6, 9 divided by 0.018. Hopefully I entered that correctly into my non-scientific calculator. I have the separation between the slits is equal to 1.27 times 10 to the minus 4 meters, or 127 micrometers. So you might double check my calculation because I did not use scientific notation. Anyone can make a mistake with zeros. So there's an example of using a double slit calculation. Practical example, or practical situation. The laser is used to eliminate two narrow parallel slits. Once again, I would have shown you this in class. The interference pattern is observed on a distant screen. What happens to the pattern observed if the distance between the slits is decreased? So distance between the slits, that's the lowercase d. Answer, we know that d sine theta is equal to m lambda. So sine theta is m lambda over d. So if d decreases, then sine theta increases. Sine theta increasing means the spacing is getting bigger, so the spacing will increase. And once again, I would have demonstrated that in class. Now, diffraction gratings are not just one slit, but lots of slits with the same, I know, like my D is cut off here, with the same spacing between each slit. The reason for a diffraction grating is actually real simple. If I have just two slits, then my pattern looks something like this, where we have this place here was perfectly in phase, and then this was partially in phase, partially out of phase. Partially in phase, partially out of phase there. Perfectly out of phase there. That's with two slits. But if I had a third slit, the third slit would once again have these relationships, but it would make it so it's narrower here because you'd have more out of phaseness unless you're right on in phase. So if you make a diffraction grating with hundreds or thousands of slits, it turns out that everywhere except for the exact angle where it's in phase, you have essentially randomized phase, So it averages out to destructive. So with a grating, everywhere is destructive except d sine theta equals m lambda. So you don't have a destructive interference equation. You just have the constructive interference equation. Every place else is destructive. So if I were to show you this in class, you would have seen just a bunch of pinpoints. Because I use a laser beam that's a pinpoint, you'd see a bunch of pinpoints and no fuzziness, no bands. So that's why in research we use diffraction gratings, or its cousin, my brain just went blank. You have a reflection grating, where instead of having slits, you have mirrors. The reason for the reflection grating is you have the light comes in and all of the light that hits here remains in phase. So you didn't lose any light. This light here comes out like this. You don't lose any light, so your intensity is much greater with the diffraction or with the reflection grating than with a diffraction grating. But they do the same thing in terms of it's constructive if you're exactly at that angle, destructive for any other angle. Just some basic things to remember. More slits lets more light pass through, so it's brighter. And you have very narrow maxima. And well, that's all I want to talk about there. In this picture, we have a spectrum. We had white light that went through a grating, and it gave us all the colors of the rainbow. You see the edge, infrared. If you go beyond this, you're into infrared. Here, ultraviolet. If you go beyond violet, you're in ultraviolet. We see all of the colors of the rainbow are in that white light. And you actually are supposed to be able to do a calculation from this, but we're going to skip over that because you have to, say, oh, well, we were able to get the first order set here, and then the second order goes out to around here, and we have an overlap that the third order started here, and we're getting out to green in the third order. So green is, let's say, around 450 nanometers at theta 3 equals 90 degrees. And that's how you calculate. You have the wavelength is 450 nanometers. The angle is this. And d sine theta 3 is equal to 3 lambda. So you know this angle, sine of 90 degrees is 1. And actually, I said we weren't going to do it. Well, we're done now. 3 times 450 is 1350. And so that's the spacing between the slits. The spacing between the slits. Now, it said number of slits per centimeter. So if I have 1,350 nanometers between the slits, then I have 1 slit per 1,350 nanometers is the spacing. And so number of slits per centimeter, well, I just multiply this by 10 to the 7th nanometers per centimeter. And that would give me my number of slits per centimeter. Spectroscopy is based on this. Spectroscopy is breaking light up into the colors that are present. And so in class, we would have shown you like a hydrogen vapor lamp, and we'd see the specific colors in the hydrogen vapor. It's not a continuous spectrum. Or helium vapor lamp. We can also use this to look at the sun and see the specific colors that are present or absent from the sun's radiation or other stars. And by analyzing that, taking the idea that hydrogen has certain colors, helium has certain colors, when we look at stars, we can actually determine compositions in their atmosphere, as well as, well, there's a number of things we learned from spectroscopy, but we'll leave it at that for today. So it's very important for understanding light, and especially in astronomy where light is all you have to analyze. Reflection gratings are talked about here. Final thing, I hope, is a single slit diffraction. Double slit diffraction, that was actually pretty simple. When you get down to it, it's pretty simple. Single slit diffraction is a little more complicated. Ask David Chapman after Tuesday's class, and he'll say a lot more complicated. So another thing in our terminology, we had D, lowercase d was the separation between slits. Now we're going to use a lowercase a for the width of a slit. Now, if I have light going through a single slit, you get to a single point on the screen over here. The distance from one side of the slit is not the same as the distance from the other side of the slit. And so you can have constructive or destructive interference between those two lines I drew. But you have a continuum of light coming through here. So how do you analyze that? Well, the first thing we do is we say, okay, what condition is going to give me destructive interference? And if I take my slit and I break it into two halves, so I have the first half shown there, second half here. And if I take this and I take a ray halfway in between, if these two are destructive, then for every ray in the top half, there is a destructive ray in the bottom half. And thus it's going to be destructive. And so based on this geometry, this is 1/2 a to get to the halfway point. And so that means the path length difference is 1/2 a sine theta rather than a sine theta for those two. And for that to be destructive, I have delta L is equal to m plus 1/2 wavelength is equal to 1/2 a sine theta. And so, well, what do we do with this? We multiply everything by 2, generally speaking, and we would have 2m plus lambda equals a sine theta for my situation. 2m lambda plus lambda is equal to a sine theta. That would be the equation there, and it just doesn't feel right to me because I know it comes out to be we take the case, well, that's how I don't want to sit and argue about it. This here is the relationship we get for destructive interference. I'm trying to look and see what happened with my math there, but I know that that's the correct equation, the outcome. And so we only calculate for this level the destructive interference places, The constructive interference places actually don't have so simple of an equation. Oh yes, I know why this came out funky. It came out funky because this is only talking about splitting it one way. You could split it other ways and have a similar situation. So in the end, if a sine theta over lambda is equal to an integer, it's going to be destructive mouse. So this is what it actually looks like when you have a single slit. Now, oftentimes we tend to think, this here must represent how wide the slit is. But that's not true. That central fringe is going to be, of course, x is equal to d tangent theta, where tangent theta comes from this. And notice if lambda gets smaller, or excuse me, if a gets smaller for a given lambda, then theta has to get bigger. So the smaller the width, the broader your central peak is going to be. So a really narrow slit will give a very broad central maximum. Whereas if you have a broad slit, it gives a very narrow central maximum. So a question I always like to talk about is you might go to, let's say, the county fair. And the county fair, you see they have speakers set up like yeah. And the question is, should it be oriented like that or like that? The answer is, where do you want the sound to be dispersed at the county fair? Well, you want the sound to be dispersed horizontally. And so the narrower it is for the horizontal aspect, the broader it's going to be horizontally dispersed. The broader it is for the vertical, the narrower it's going to be dispersed. So if you have it oriented like this, you're going to cover not much vertical range, but a whole broad horizontal range. So your sound doesn't go up into the air or down into the ground. It just goes out horizontally, but it's going to the left and to the right as much as you can so that people can hear all over the fairground. Okay, one last problem. The diffraction pattern from a single slit of width 0.020 millimeters is viewed on a screen. If the screen is 1.20 meters from the slit, so obviously you need a picture. I'll draw the picture here and then go down. So we have a slit like this. A equals 0.020 millimeters. And then we have a screen out here, capital D equals 1.20 meters. And we're given wavelength is 430 nanometers. And I want to know what the width of the central maximum is. So that's going from m equals 1 to m equals minus 1. Now remember, x is equal to d tangent theta, just geometry. And in this case, I don't know offhand if it's going to be small angle or not. So I'm not going to apply the small angle approximation just because I don't know. And I could probably figure it out, but why worry about it? So here's one equation. That's just geometry. And then we have for our minima, a sine theta m is equal to m lambda. So let's calculate theta 1. Theta 1 is equal to inverse sine of 1 times lambda over a. So my wavelength here is 430 nanometers. And my spacing is, now keep in mind, a equals 0.020 millimeters. So that's 10 to the minus 3. Move this over 4, 5 equals 2.0 times 10 to the minus 5 meters. Or 2.0 times 10 to the plus 4 nanometers, because nanometer is 10 to the minus 9. So over 2.0 times 10 to the 4 nanometers. I wanted them both in the same unit just so I could do my trig function. So clear 430 divided by 20,000. And then I do inverse sine. And that's, sure enough, that's a small angle, 0.0215 radians. Trust that's in it's radians. And if you do this thing right here, that's 0.0215. So it is a small angle. Then I come over here and x is equal to d, which is 1.20 meters, times tangent of 0.0215 radians, which is just 0.0215 again. So I take that and multiply it by 1.2 meters. I have 0.0258 meters is x. Well, the width is 2x because you have x going out to -1 and x going out to +1. So the width is equal to 2x is equal to 0.0516 meters. All right. If you have a double slit, the intensity is actually the envelope of the single slit and the double slit patterns. So the dark color is the reality. The double slit would have not dropped down so much. The double slit would have gone, actually the double slit would have just by the equation gone like this the whole way, going all the way to the top. But the amplitude is modulated by the single slit calculation. So here you have the first minimum for single slit that actually corresponds in this picture pretty much to the fifth maximum for the double slit. And so you have no light at that maximum because the intensity is modulated by the single slit. Now, the end thing, what if we have a circular hole? We have been talking about a single slit, but it was a rectangular slit. What if it's circular? Well, the same ideas apply. You can see from this picture, it's not exactly the same, but you have a central maximum. So here's your central maximum, and then you have a minima, and then you have a second maximum, minimum, third, and so on. And it turns out that the first minimum occurs when A, where A is okay, now I have to go back. I think A is the diameter. I want to make sure. Yeah, where A is the diameter of the circle, A sine theta, the angle for the minimum, is 1.22 times the wavelength. Why is this important? Well, with optical instruments like with a telescope or a microscope, you want to try to resolve two things that are a small angle apart. Resolve means you can tell that there's 2 points. But if you have diffraction, you kind of have a big fuzzy point, and you can't tell the difference between this being a bar and being 2 points. So Rayleigh's criteria is a way that we use to say this is probably our optimal resolution. If you have the maximum of one occurs at the place of the minimum of the next, then we say these are resolved. So this picture doesn't quite show it because it shows the maximum of one at the maximum of the other instead of minimum. But that's his criteria. And so, because the angle depends on the wavelength and the size of the hole, if you have a smaller hole, the angle gets bigger, which means you can't resolve as much. If you have a bigger hole, then the angle gets smaller, right? If A goes up, then theta goes down, and you can see more detail. So with a telescope, you want to have a really big objective because you will have a smaller amount of diffraction that occurs and you can see finer detail. So bigger is better with a telescope, everything about it. A bigger telescope gives you better resolution. It also collects more light. The only thing that's not good about the bigger telescope is it's heavier and harder to handle. And that ends the lecture. Have a great day.